Hi everyone, welcome back to Introductory Physics, day 14, I think. We are going to finish up chapter 6 today and then move into chapter 7. We won't finish chapter 7, but we'll get started on that at least. So, without further ado, we have a give it a try example. So, here we go. Two ice boats hold a race on a frictionless horizontal lake. The two ice boats have masses n and 2m. Each ice boat has an identical sail, so the wind exerts the same constant force F on each ice boat. The two ice boats start from rest and cross the finish line a distance S away. Which ice boat crosses the finish line with greater kinetic energy? Take a second. What do you guys think? So thinking about this, we know that mass does affect the kinetic energy that something has, right? Kinetic energy is 1/2 times mass times velocity squared. So as we think through this, though, we have to remember that kinetic energy is also, thanks to that work energy theorem, kinetic energy equals the total work done to accelerate that boat, that ice boat, from rest. And we know from yesterday as well that work is force times your displacement. So if we have the same constant force on each boat and they're covering the same displacement, then they actually have the same kinetic energy. The red one gets there first. It goes faster because it has less mass. It has more acceleration. Remember Newton's second law? Net force equals mass times acceleration. So if they have the same force and one has a smaller mass, then it has to have a bigger acceleration. So the red boat will win. It will cross the finish line first, but they will both have the same kinetic energy as they're crossing the finish line. Ah, right. Okay. So power. Um, we tend to use this word as well in like real life in the wrong in according to physics in the wrong ways, just like we do with work or distance. We use those incorrectly in real life. So the thing about work that's kind of annoying is that work doesn't depend on time directly. And I say it doesn't depend on time directly because work does depend on force, which depends on acceleration, which depends on time. But that's really a convoluted way. There's no equation for work that involves time explicitly. So sometimes that's really convenient, and sometimes it's not. So if you lift a barbell, again, going back to working out and getting swole or whatever you want to do in your free time, if you lift a barbell weighing 100 newtons through a vertical distance of 1 meter at a constant velocity, you do 100 joules of work. Whether it takes you 1 second, 1 hour, or 1 year to do it, you have done the same amount of work. So, if it takes you a whole hour to lift a barbell up over your head, congrats, you did the same amount of work as that bodybuilder next to you who did it in half a second. Yay, go you. Of course, your power is not the same. You're not exerting the same amount of work each second that bodybuilder would do. So usually we want to know how quickly that work is done, and that idea, that rate of work is called power. So the symbol for power is capital P, and the unit is watts, which is capital W. Now, careful here because the symbol for work is also capital W, and those two things are like work and watts. We're using them in the same chapter, just like we did with normal force and newtons, which are the symbol capital N. We are just running out of letters here, so just be careful about whether you're using W as a variable for work or as a unit for watts. But regardless, 1 watt is 1 joule per second. We can also sometimes use the unit of horsepower, which is HP, and that's equal to 746 watts. Power, just like work, is also a scalar. So there's no direction associated with power. All right. And just like we did back in chapter 2 when we were dealing with velocity and that sort of thing, we'll have an average power and an instantaneous power. So average power is the work divided by the change in time. It's the rate of the work. But we also know that work, thanks to the work energy theorem, work is the change in kinetic energy. So that's delta E over delta T. But we also know that work is our force that's like, so the force with the two bars next to it is the parallel force. That's the force that's actually helping in the direction of motion, like we talked about yesterday. So the parallel force times the displacement is the same thing as work. But we also know that our displacement divided by time is velocity. So force times average velocity is also average power. Instantaneous power, since we're dealing with this, like delta E over delta T, it's a rate of change of something, how fast your work is changing over time. That means it's also a derivative. So instantaneous power, just plain P, is the limit as the time interval approaches 0 of our change in work over change in time, or the derivative of work with respect to time, or our parallel force times our velocity, or our F dot V. Remember, this symbol right here is called a dot. We like literally say dot, F dot V. It's not multiplied because we have these two quantities, force and velocity, which are vectors, and we have to treat them in a special way when we multiply them together. So just like we talked about yesterday, doing a dot product basically tells us how much our force is parallel to the direction of motion. So this would be how much of our force is parallel to our velocity vector. I'm so happy that I could make you happy with that, Jeff Colby. You're welcome for that. Okay. Anyway, these, I say two equations, but really it's like a string of equations. But these two sets of equations, I suppose, are going to be really helpful for you. And I wanted to include all of the possibilities because depending on the particular scenario, you might be given a force and a velocity, you might be given an energy and a time, and you can calculate the average power from those, whatever pair you have, if you know how to do it. So I wanted to list those all for you, but you probably won't use all of them in a particular scenario. You just choose whatever is most convenient. Okay. So example 4, each of the two jet engines in a Boeing 767 airliner develops a thrust. Thrust is a forward force on the airplane of 197,000 newtons. When the airplane is flying at 250 meters per second, what horsepower does each engine develop? So thrust is in the direction of motion. It's like the force of the engines propelling it forward. So that means that our force is, well, the force that's parallel to our direction of motion is the entire thrust. It's equal to the whole value of the thrust because it's in the same direction. So that means our power is our parallel force times our velocity. So I put our force in scientific notation, just a quick review what that is like, because we haven't really done that since chapter 1. So remember, we take our decimal point, move it over until it's behind the first non-zero digit, and then the exponent is the number of decimal places that we moved it over. And since we moved it to the left 5 places, our exponent is positive 5. So 1.97 times 10 to the 5th is the same thing as 197,000. Our velocity is there, 250 meters per second. So that gives us a power of 4.93 times 10 to the 7 watts. but we didn't want it in watts, we wanted it in horsepower, so now we have to do a unit conversion. Yay, everyone's favorite. So again, I set them up as ratios just so we can easily see how our units are going to cancel out when they're on top and on bottom. So here's the quantity that we're starting with, our result from that calculation. And on the previous slide, I told you that 1 horsepower equals 746 watts. So we put 746 watts on the bottom so that watts on top cancels watts on bottom. And then we're left with the unit that we want, which is horsepower. So we take this top number divided by the bottom number, and that gives us our answer of 66,000 horsepower. Pretty significant. I don't know what this plane actually is, but I just Googled an image of a Boeing 767. That's what it came up with. Okay, another example, a power climb. A 50-kilogram marathon runner runs up the stairs to the top of Chicago's 443-meter tall Willis Tower. It used to be called the Sears Tower. Everybody in Chicago still really calls it the Sears Tower, but it's actually renamed the Willis Tower. And it was formerly the tallest building in the United States, but then they rebuilt the World Trade Center. I forget what it's actually called now, like the One World Trading Center or something like that. I don't know. Anyway, to lift herself to the top in 15 minutes, what must her average power output be in watts, in kilowatts, and in horsepower? So you can see right there, since I'm asking for 3 different kinds of units, we're going to do some more unit conversions. Yay! Don't hate me. So there are 2 strategies that you could use to solve this problem. I'm going to walk through both so you see both ways. First, we can determine how much work she does and then divide it by the elapsed time. Or we could calculate the average upward force that she's exerting in the direction of her climb and then multiply that by the velocity. So we'll do both. Starting with strategy 1, figuring out how much work she does, then divide it by the elapsed time. Well, let's think about what force we're dealing with and what energy that's associated with. So lifting a mass against gravity, herself being the mass, requires an amount of work equal to the weight, the force of gravity, multiplied by the distance, well, the displacement or her height that it is lifted. So the work that she is doing, remember force times displacement, force of gravity times height, mgh, gives us an answer of 2.17 times 10 to the 5th joules. The time elapsed is 15 minutes, which, if we convert that to seconds, ends up being 900 seconds. So the average power is 2.17 times 10 to the 5th joules divided by 900 seconds, or 241 watts. Remember, to go from watts to kilowatts, you divide by 1,000. Kilo is one of those prefixes that you should know off the top of your head. So if you've forgotten how to do those in the past 3 weeks, just take a quick refresher, maybe tonight, and look through those metric prefixes. And then doing the same sort of unit conversion that we just did in the previous example, we can go from watts to horsepower, because 1 horsepower equals 746 watts. And so we get our answer of 3.23 horsepower. Okay, so that's method 1. And just in case you want to see how we did those unit conversions, if you go back and look at this video or the slides once I post them to Canvas, I have laid out here how we did the unit conversions, because I know some of you guys said that you needed more practice with them, or you just hate them to the end of the earth. But anyway, here's how I did it, right? 241 watts. We know 1 kilowatt is 1,000 watts. We put watts on top and bottom so they cancel out, and then we get our answer in kilowatts. And then same sort of thing going from watts to horsepower. We set up that ratio, 1 horsepower equals 746 watts. Watts will cancel out, we're left with horsepower, and that's how we got our answer. Okay, strategy number 2, calculate the upward force that she must exert in the direction of her climb, and then multiply that by the upward velocity. So the force that she's exerting is vertical, and the average vertical component of the velocity is her change in position, her displacement, divided by the time interval. So we know the height of the building, 443 meters, and the time we found in the previous part, so I didn't bother doing it again. That was 900 seconds. So that gives us a velocity of 0.492 meters per second. And now our average power is our parallel force. Remember, parallel meaning it's in the same direction as her motion, times her average velocity. So again, the force that she is fighting against, that's kind of in the direction of motion there, is the force of gravity. So that's mass times g times her average velocity. And that again gives us 241 watts, which is 0.241 kilowatts, which is 0.323 horsepower. So either way we did it, we got the same answer, which is a great way for you to check your work and make sure that you got the right answer, right? We should always be evaluating our answers to see if we're correct. So there we have it. Any questions about either of those two examples? Oh, good. Why would she be running up the stairs? Wouldn't she be running 26 miles on flat ground? Yeah, I wouldn't necessarily, like if I'm training during the winter in Chicago, I would not be running outside. I'd be looking for stair sets that I could run up. But that's also really good cardio anyway, so go her. I'm not about to do that, but you do you. Okay, so then I want you to give this a try. An elevator rises at 0.9 meters per second and can lift 1,200 kilograms. What is its power? Or should I say, what is its power? A. No? Okay. You didn't like my pun. So sad. Okay, so take a second, try to solve this problem on your own, and we'll come back and do it together. All right. So just like we've seen in the previous couple examples, power is our parallel force times our velocity. The force that's acting in this scenario is again gravity because the elevator is rising against gravity. So our force is mass times g. Our velocity will also factor in. So mass is 1,200 kilograms. G is 9.8 meters per second squared. Velocity is 0.9 meters per second, and that gives us a power of 10,600 watts. You could put that into kilowatts if you would like to. It'd be 10.6 kilowatts, but I didn't ask for a specific unit, so you are welcome to leave it in watts as well. You overthink things because you've been scarred. Yeah, that happens. Okay. Any questions about power versus work versus kinetic energy, anything that we've talked about in chapter 6? Speak now or hold your peace until you can type it in the chat. Lol. Okay. Well, I am gonna move on then to chapter 7. So let me go ahead and switch PowerPoints. One moment, please. So as I get there, in case you're wondering about power and that sort of thing, power relates to energy like I just told you in the PowerPoint. And when we're talking about energy, we often talk about kilowatt hours. which is not the same thing as power, it's an energy. Kilowatt hours is a unit of energy. But 1 kilowatt hour costs about 10 cents in Florida. So that's like running 10 100-watt light bulbs for an hour. Or you could run your refrigerator for 2.5 hours. Or you could run your air conditioner for 30 minutes. That's all the same, approximately the same amount of energy, 1 kilowatt hour. So, every 30 minutes that you're running your AC in Florida, it's 10 cents on average. And every 2.5 hours that pass that your refrigerator is plugged in, that's another 10 cents. So once you actually have to pay your own bills, you'll find that it adds up really quickly, which is unfortunate. Okay. Well, anywho. Slideshow. All right. Can we all see the potential energy and energy conservation PowerPoint? Yes, we can see it. Great. Only eat canned goods. Yeah, I mean, ramen still, like, you have to either use a microwave or an oven, which uses power. So there's that. Okay. Just PB&J, maybe. Actually, I guess jelly has to be refrigerated. Just peanut butter sandwiches. Only peanut butter. That's true. Leave it under the Florida sun for a minute. Yeah, that would do it as well. Anyway, we're gonna move on to different types of energy. We'll be talking about this topic today and tomorrow, and what day is it? Tuesday, possibly even more on Thursday. This is like next to Newton's laws. This idea of energy and conservation of energy is like one of the most foundational things in Physics 1, and it's one of the most important topics to really make sure that you understand. I think when a lot of people think about Physics 1, they either think about Newton's laws or projectile motion or energy. And so we've done projectile motion, we've done Newton's laws. This is our next like really, really important topic that we'll be talking about. But one of the nice things about energy is that energy is a scalar. So for a little while, we get to take a break from vectors. Woo! I mean, maybe that like doesn't really phase you at all, but here we go. Okay, so back to the work energy theorem, because they're still related to each other, work and energy. So we just talked about in chapter 6 that the total work in a situation is the change in kinetic energy of that particular object. And the total work depends on all of the forces that are involved. We did an example like that yesterday where we calculated the total work due to all of the different forces, the work that all of those different forces did on the sled of firewood. We added them all together to get the total work. So it depends on all of the forces that are involved. And for example, your total work might be something like the work due to gravity plus the work due to a spring force plus whatever other forces you might have. Other tends to be like friction or air resistance or an applied force, something like that. And we'll talk about springs later. I'm going to just introduce one thing at a time. But anyway, all of those things added together gives us our total work, which is then equal to our change in kinetic energy. So today we're going to figure out what the work due to gravity is. Woohoo! So remember, the force of gravity is mass times g, and we're assuming that it's pulling down. So that means the work due to gravity is force times displacement times the cosine of the angle between the force and the direction of motion. That's true of all work, whether or not it's gravity. So if something is falling straight down, that means the force of gravity is down and the displacement is down. So the cosine of our angle is +1. And the work done by gravity, in that case, is just force times displacement then. again, because the cosine of an angle is 1, then force times displacement times 1 is the same thing as force times displacement. And we know the force is mass times g. So the work done by gravity is then mass times g times displacement. If you're lifting something straight up, the force of gravity is still down, but now your displacement is up. And that's a 180-degree difference between the force and the direction of motion. So the cosine of 180 degrees is -1, which means in that case, the work done by gravity is negative F times displacement, or negative mass times G times displacement. So remember, as an object falls down, the work due to gravity is positive because gravity is helping it fall down. If you're lifting an object up, then the work done by gravity is negative because it's opposing that motion. It's not helping you lift it up. So if we want to define gravitational potential energy, it's often really inconvenient to just talk about the work done by gravity. So we tend to look at gravity a different way, and that's using gravitational potential energy. So gravitational potential energy is the energy that an object has due to its position. Remember, kinetic energy is the energy something has due to its motion. Kinetic means motion. So gravitational potential energy is the potential of an object to fall down because of gravity. So if something is on the ground, then it has no potential to fall anywhere, and so its gravitational potential energy would be 0 if the ground is your 0 point. If you lift something up a little bit, it has the potential to fall down a little bit. And if you lift something up a lot, it has the potential to fall down a lot. So the higher you lift something up, the more potential it has to fall, and the more gravitational potential energy it will possess. Just like with kinetic energy, we have a lot of different symbols that you might see for gravitational potential energy. You might see GPE or just PE for potential energy. You might see just U, but most commonly, I think you'll see U sub G or U sub grav. U means potential energy because we just used P for power. So I think that's why professors and textbooks tend to kind of shy away from using PE, and they go in favor of capital U, although I really don't know what that has to do with gravitational potential energy. Like, why'd they choose U? I guess it was available. The units of joules, the units are joules, just like with kinetic energy and like every other kind of energy that we'll be dealing with. And the equations, we have the potential energy due to gravity, U sub G. You might see it written as mgh, h meaning height, mgy, y meaning vertical position, mgd, d meaning distance from your 0 point, or you might just see delta U G, so the change in our gravitational potential energy equals mass times G times the change in our Y position. All of those are equally valid, and every textbook, every class, every professor does it slightly differently. It's the same concept, but they use that slightly different variable. So I want to make sure that you have exposure to all of those different ways to write it. But all of these, whether you're using height, H, vertical position, Y, or distance, D, all of those mean a vertical position relative to a 0 point. So you can choose the 0 height to be wherever you want, wherever it's most convenient, just like we did in projectile motion. The difference in the height will not change no matter where you set your 0 points to be. So pick whatever's most convenient. Potential energy is relative. There's not an absolute amount of it. It's just more or less of it than somewhere else. So if you wanted to, you could pick your 0 point to be like the surface of the moon. I'm not sure why that would be helpful in most cases, but you totally could and it would be valid. You could choose the center of the earth. You could choose your neighbor's house, or whatever. Your change in distance from that is not going to change, no matter what 0 point you use. So pick whatever is most convenient, whatever floats your boat. Okay. So example 1A. Determine the change in potential energy of a 2 kilogram book as it falls 1 meter from the top of a table to the ground. And this time we're going to take the ground as our 0 point, y equals 0 meters. And as we go through this, I want you to think, does it gain or lose potential energy as it falls? So here's our table and our floor and our book. It is going to fall down. So we said take the ground as y equals 0, which means the height of the book is our position of 1 meter, because it says it's 1 meter from the top of the table to the ground. So thinking about our potential energy then, our change in gravitational potential energy is the potential energy at point 2 minus potential energy at point 1, just like every other change in something that we've ever calculated. So if we know that the potential energy due to gravity is mgy in this case, then our change in potential energy is mgy2 minus mgy1. Plug in our numbers. We know our mass is 2 kilograms, g is 9.8. Our y2 is 0 because that's where it ends up. And our y1 is 1 meter because that's where it's starting. And so that gives us a change in potential energy of negative 19.6 joules. So does it gain or lose potential energy as it falls? It loses potential energy, right? Because as it falls down, it doesn't have more potential to fall down to the ground. It gets less potential to fall down to the ground. And once it's sitting on the ground, it has no potential to fall down to the ground because it's already on the ground, right? So it's losing potential energy as it falls. What is it gaining though? Bonus question. Kinetic energy, right, Colby? It's gaining kinetic energy because as it falls, it's going to get faster and faster and faster. And we know that the velocity, well, kinetic energy depends on velocity. So it'll gain kinetic energy as it loses potential energy. Example 1b, now same scenario, but let's take the top of the table as our 0 point. So here y equals 0 is where the book starts. That means it'll end up at a position of negative 1 meter because it fell down 1 meter. So the same setup, right? Our change in potential energy is the same potential 2 minus potential 1, which is mgy2 minus mgy1. Now our y2 is negative 1 and our y1 is 0. But we end up getting the same result. Our change in potential energy is still negative 19.6 joules. So that just proves, whatever 0 point you want to take for your height, it doesn't matter. You're still going to get the same change in your potential energy because it's all relative to that 0 point. So pick whatever floats your boat. Usually I'll pick the ground to be 0, just because that makes more sense in my head. But as you see, you can choose whatever you would like. Gravitational potential versus work. So as an object falls down, we just talked about how it loses its potential energy. Its change in potential energy is negative, just like we saw in that example 1. Which means as well as an object is lifted up, it's getting more potential energy due to gravity. So its change in potential energy is positive. But also, as an object falls down, the work due to gravity is positive because the force of gravity is pulling then in the same direction as its motion, and vice versa, like we had talked about previously. If you're lifting up an object, The work done by gravity is negative because gravity is in the opposite direction as its motion. So that means that our change in gravitational potential energy equals the negative of the work done by gravity. That's another really important equation for you to maybe write down on an equation sheet if you're keeping track of these things. But that negative sign is essential. You cannot forget it, right? You can't forget it. So for now, we're just thinking about when gravity is doing work on an object. So we're not considering things like air resistance and friction and other stuff. We'll get into that in a couple of minutes. So right now, just think about when gravity is doing the work on the object. So we just saw on the previous slide that our change in potential energy is negative the work done by gravity. And we can take that negative and just move it over to the other sign of the equals sign. It means the same thing. You'll see why that's helpful in just a minute. We also had mentioned earlier that the total work done equals the change in kinetic energy. And previously we had also mentioned that the total work is from all of the forces that are acting on a particular object. So we could have work due to gravity, work due to springs, work due to other things like friction or applied forces or air resistance. I haven't taught you about springs yet, so we're going to put a pin in that and save that for later. And same thing with the other stuff. We'll get into that more later. But if we know then that the work due to gravity is negative times the change in potential energy, we'll just sub that in there. So that means negative change in our potential energy plus the work due to other things equals the change in our kinetic energy. So our work due to other things equals the change in kinetic energy plus our work, our change in potential energy. And we call that change in total mechanical energy. Capital E, just by itself, means total mechanical energy. So this is another one of those really important equations to keep a mental note of. But also, if our total work is the change in kinetic energy and total work is the work due to gravity, which is the opposite of the change in potential energy, again, we're saying that second chunk is true because we're just thinking about when gravity is doing the work. So we're ignoring the other for now. Then our change in kinetic energy, K2 minus K1, equals our change in potential energy. But remember, there's that negative sign in there. So K2 minus K1 equals UG1 minus UG2 because there's that negative sign that we distribute. Anyway, we can then rearrange this equation to get K1 plus UG1 equals K2 plus UG2. And that is another really important equation. I'll pause there for a moment in case you want to write it down real quick. But we'll be using this equation quite a lot in the next couple of days. Okay. So total mechanical energy, that symbol capital E, the sum of our kinetic energy and our gravitational potential energy is called E, the total mechanical energy of the system. So there it is again. E is K plus our potential gravitational energy, and that is actually a constant, right? We had just talked about in example 1, I think, yeah, that as it loses its potential energy, it's gaining kinetic energy. So that number is going to be a constant, and that's really, really helpful for us. And one of those most important laws of nature that we've seen so far. So when something always has the same value, when it's a constant like that, it's called a conserved quantity, because to conserve something means to save it or to keep it the same. So this is really our first equation of conservation of mechanical energy. And we'll come back and edit this equation a little bit as we go. So you'll see how it changes throughout the next couple of days. But when you throw a ball into the air, just for another example, on the way up, the speed decreases. So it goes from having a lot of kinetic energy to a lot of potential energy as it goes up and up higher. And so our change in kinetic energy is negative because it's slowing down. Velocity is going from big to small. But our change in potential gravitational energy is positive, right? It's going to a higher height. On the way down, the opposite happens. The speed increases, so that potential energy turns into kinetic energy. So our change in kinetic energy is positive, and our change in gravitational potential energy is negative. But the total energy is the same at every single point in that ball's path. All right, example 2, throwing a baseball. You throw a 0.145 kilogram baseball straight up in the air, giving it an initial upward velocity of magnitude 20.0 meters per second. Find how high it goes, ignoring air resistance. Again, air resistance would be a other category, and we're just not there yet, so we'll ignore it for now. Okay, so here's the picture supplied by the textbook. Okay, it's in our hand, we're throwing it up, and at some point, the velocity will be 0 right before it comes back down. We talked about that in projectile motion, chapter 3. So I'm going to take point 1 to be the level of your hand and point 2 to be at the peak. You could also call them initial and final. So the initial point is at your hand and the final point is at the peak. Whatever you want to call them is fine. So at point 1, our gravitational potential energy is 0 because it's in your hand. It doesn't have the potential to fall any closer to your hand. It's in your hand. So our gravitational potential energy is 0, has 0 height. At point 2, the ball is as high as it can go before it changes direction. So our velocity is momentarily 0 at that point, right before it changes direction, which means our kinetic energy at that point is momentarily 0. Those things, recognizing those things in a situation will greatly simplify your math. So in any problem like this that you do, make sure you take a couple of minutes and think through any how you can make convenient points like that in your problem. So if we think about our conservation of energy equation, where our kinetic energy plus potential energy at first equals our kinetic energy plus potential energy at the end, well, potential energy at the beginning is 0, kinetic energy at the end is 0, so those things are going to factor out in our equation. Right? Kinetic energy is 1/2 mv squared. Potential energy is mgy. And you can see that in both of those terms, we have mass. So since they're on the opposite side of the equal sign, we can cancel out both of those masses. And we don't even need to know the mass of our baseball at all. Woohoo! So I took that equation and I rearranged it to solve for the height, which is v1 squared over 2g. So once we plug in our numbers, we get a final height of 20.4 meters. Now you could have done this with projectile motion equations as well, but energy tends to be the simpler way to go if you're debating between kinematic equations and energy. Usually go with energy, unless you need time, because time doesn't really factor into these energy equations. Okay, So now we're at the point where forces other than gravity could be affecting our object, right? So now our total work done on our object is the work due to gravity plus the work due to other things, again, like applied force or friction or air resistance. And according to our work energy theorem, that still equals K2 minus K1. So our conservation of energy equation becomes K1 plus potential energy 1 plus the work done by our other stuff, our other forces, equals K2 plus UG2. So the work done by all of our forces other than gravitational forces equals the change in the total mechanical energy of the system. Okay, so if that other work, friction, applied force, etc., if that's positive, then our energy is increasing because that's like we're pushing it in the same direction that it's moving. So that's going to make it move faster. So our energy increases and our final energy is going to be more than our initial energy. If our other work is negative, that's like air resistance or friction trying to slow it down. So our energy decreases and K2 would be less than K1. I'm sorry, energy 2 would be less than energy 1. If there are no other forces than the body's weight, so we just have work due to gravity, then our work due to other things is 0. And so our energy is constant like we saw previously. Okay, so in these cases, just like I outlined a good problem solving strategy for you with projectile motion, and I think I did with Newton's laws as well. There are specific problem solving strategies that could be helpful for you when you're looking at energy type problems. So again, following that model laid out by the textbook, we're going to identify, so we'll decide whether we're going to use energy, Newton's laws, or kinematic equations, or a combination of all of these things. Energy approaches best if the problem involves forces that are varied, or if we're moving along a curved path, or that sort of thing, because thinking about that for kinematic equations, those are kind of complicated. If the problem involves time, though, energy is usually not the best choice, again, because we don't explicitly have time as one of the variables in our equations for energy. When we set up the problems, we're going to first decide what our initial and our final states of the system are. So you can either use subscripts 1 and 2 like I've been doing. You could use I and F for initial and final. But it does help you if you draw a picture, like I've been saying all along. Draw a picture. It will help you figure out what the best choice of those things would be. Always define your coordinate system and pick a zero height that's most convenient. And I would say, like previously, when we were doing Newton's laws and applying those, we said, we said that you can choose down to be positive if you want to, and up to be negative. But in these cases, when we're dealing with energy, it's best to always choose positive y direction to be up, because that's the assumption that all of our equations are based on. And so if you choose down to be positive, then you'll have to rederive your equations, and ain't nobody got time for that on a test. Identify all the forces that are doing work that cannot be described in terms of potential energy. So sometimes a free body diagram can be really helpful here in figuring out what forces are acting on your object, what things are considered other or external forces, etc. And then it's helpful to list all of the things that you know from the scenario, what things you're looking for, all that jazz. Figure out your target variables. To execute the problem, you're going to write the expressions for initial and final kinetic and potential energies. And then we're going to relate those with the work done by other forces, just like we saw previously. It's sometimes helpful to draw bar graphs that show how your energy changes from like one kind to another. So from kinetic to potential or potential to kinetic throughout the problem. I will show you an example using those energy bar graphs, but I don't think that you really do those in college physics. I don't know if you did them in high school physics. Sometimes I made my students do them. Just if they're having trouble visualizing what was happening to the energy, then I would recommend that they draw the bar graphs. Um, you may or may not need to use that skill, but I'll show you how to do it anyway. And then, of course, you want to solve your equation to find whatever is required of you. And lastly, we're going to evaluate your answer to see if it makes sense. So the work done by each force needs to be represented either in the potential energy of gravity or in that other category, but never in both places. So since we're including gravity in the gravitational potential energy, we do not also include it in the work due to other things. You just include it once. Okay, so here's another example. I fire a cannon from the top of your 18.5 meter castle. The cannonball is shot at 130 meters per second. How fast is it going when it hits the water below? This is another case where you could use kinematic equations if you wanted to, but energy is actually um, simpler to do in this case. So here's our castle with our cannonball and the water below. It'll follow this nice curved trajectory downward like we saw in chapter 3. And we're given that it's traveling at 130 meters per second initially. The height of our castle is 18.5 meters. And I am going to choose the water to be my 0 point. So our change in energy is due to work because air resistance is a government conspiracy. Lol. So I'm sure. This is how we're starting, right? Our change in energy is the work energy theorem. So we're not really considering any other forces here. We're ignoring air resistance for now and friction and applied force. There isn't an applied force when it's falling through the air. We just have gravity. So our W other, our work due to other things, is 0. So that means that our energy, our total energy final minus total energy initial, total energy would be kinetic energy plus gravitational potential energy. And then minus, if you put parentheses around these two variables, then you would have them added together. But I just distributed the negative. So that's why this is minus here. But we have final minus initial total energies, and that equals 0. So since I'm setting the ground to be our 0 point, and well, the water, and the cannonball is ending up at the water, that means when it lands in the water, it has no potential to fall anymore. So at that point, its gravitational potential energy is 0. So we can rearrange this equation and get our final kinetic energy equals initial kinetic energy plus gravitational potential initially. So put in your equations for that. 1/2 mv squared final equals 1/2 mv squared initial plus mgy initial. And you can see in all of those terms, we have mass. So we can just cross mass out, factors out, and that's really convenient. The less numbers we have to plug in, the better. So I'm solving this for final velocity then. So final velocity squared, we take the 1/2, move it over to the other side. So we multiply by 2 on both sides. So 2 times 1/2 initial velocity squared plus g initial y Plug in your numbers. Initial velocity is 130 meters per second. Our g is 9.8, and our initial y is 18.5 meters. And that gives us a final velocity of 131.4 meters per second. I didn't include the last step of like taking the square root of the answer because it wouldn't really fit on the screen. But I did take the square root of the answer. So there we go, 131.4 meters per second. This should make some like physical sense, because if we're starting at 130 meters per second and we're shooting a cannonball pretty quickly, it's going to hit the ground pretty quickly. And so we shouldn't expect like a super small velocity. We shouldn't expect like an enormous velocity. And it's in that same ballpark as what we're starting with. So that seems to make logical sense. Okay. Any questions about this example? Okay, again, you could have done this with projectile motion if you're more comfortable using kinematic equations, but most people aren't more comfortable using those. So you can also do it with energy. Okay, so I want you to give this one a try. Example 4. Excuse me. I toss a pencil to the ceiling. The pencil hits at 3.1 meters per second. The ceiling is 2.5 meters above the floor, but I throw it from 0.9 meters above the floor. So 3 initial questions that I want you to think about before we start plugging numbers in. What is the change in height of the pencil? What is the initial velocity of the pencil? And should the mass of the pencil change how fast I have to throw it? Take a moment and think through those 3 initial questions. All right, so what is the change in height of this pencil? What did you guys get? I have a vote for 1.6 meters. Do we agree? Or are we casting Gabriel out into the storm? Marco agrees. You're safe, Gabriel, for now. Yeah, so we're starting at a height of 0.9 meters. We're ending at a height of 2.5 meters. So 2.5 minus 0.9 gives us a height, or a change in height of 1.6. So for now, Gabriel is safe. What is the initial velocity of the pencil? If you did not get this, well, if you didn't see that the final velocity of the pencil is 3.1 meters per second, that would be a really helpful thing to take note of. But figuring out what the initial velocity of the pencil is, that's a little bit more difficult to do. So we're going to do that one together. And then we'll be able to answer the question, should the mass of the pencil change how fast you have to throw it? So let's take a look. What is the initial velocity? That's the same thing as asking how fast did I throw it? So here's our picture. There's you. You have a green face today. I'm not really sure why, but I was just feeling green. Okay, so here's the room, right? You're standing on the floor. There's a ceiling. You're throwing the pencil up. It hits the ceiling at 3.1 meters per second. We know the height of the room is 2.5 meters, so I put our final height, y final, is 2.5 meters, which means y initial is 0.9 meters, and I chose the floor to be our 0 point. So we can't just say that the kinetic energy equals the potential energy, because that's not actually what the law of conservation of energy says. We have to be a little bit more specific than that. So remember, we're not considering things like air resistance and friction for these examples yet. So the work done by other things is 0. But our change in kinetic energy plus the change in the potential energy is what equals 0. So it's not that kinetic energy equals potential energy. We have to think about those triangle symbols, the change in those energies. Okay, so final kinetic minus initial kinetic plus final potential minus initial potential equals 0. I wrote out all of those equations, and we should notice that again, there's a mass in every single one of those terms. So we can factor out the mass. The mass does not affect it. We know from the scenario that our final velocity is 3.1, our final height is 2.5, and our initial height is 0.9. So when we plug all of those in, I didn't show the work for space reasons, but we get an initial velocity of 6.4 meters per second. This seems like it would be reasonable because if it's hitting with 3.1 meters per second velocity, we need to throw it faster than that because gravity will cause it to slow down as it goes up towards the ceiling. But it's still within a reasonable factor. It's not like we're throwing it at 64 meters per second. Okay. So that answers the question of how fast did I throw it? And since mass could cancel out in all of those terms, then our answer to that previous question of should the mass of the pencil affect how fast we have to throw it, the answer to that question is no, because mass doesn't really factor into these equations. I mean, it's there, but since it's in all of them and that equals to 0, then we can just take out the mass and ignore it completely. Okay, so this answers both of those last two questions. I think that's all I have for you for today. Yes. So do you guys have any questions, comments, concerns about these couple examples that we have seen today? We will do some with friction, etc., applied forces tomorrow. I'll also be talking to you guys about springs, how to consider spring force and other types of things like that. We'll do that tomorrow and Thursday as well. Will there be practice problems of these? Yeah, we'll go through more examples together. I'll do some more give it a try examples, but I'll also be posting some stuff on Canvas as soon as I can convert my files to PDFs and upload them. They will be there for you. Okay. Well, if you guys don't have any other questions or comments, concerns about the material for today, then I hope you guys have a great day and I will see you tomorrow. If you have other questions, comments, concerns, feel free to hang out for a little bit and I would be happy to answer them as best I can.